Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore a bit of each one of the 46 Hadal zones spread across the 5 oceans. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. The planet has 46 spots where the ocean floor drops below 6,000 meters. The total area occupied by all 46 individual Hadal habitats worldwide is less than 0.25% of the ocean floor. And yet these trenches concentrate more than 40% of the ocean's total depth range. There are 46 structures scattered across the planet, separated by thousands of kilometers of abyssal plains, each functioning as an isolated ecosystem. The Hadal zone extends from 6,000 to 11,000 meters deep and consists of at least 47 geographically disjunct ecosystems that dot the abyssal plains as subduction trenches, transform faults, and troughs. The name comes from Hades, the Greek god of the underworld. None of the Hadal habitats are identical to one another. Each feature varies in geomorphology, total area, maximum depth, proximity to land, hydrography, geological age, and degree of seismicity. What connects them is the same set of extreme conditions: pressure above 600 atmospheres, temperatures between 1 degree Celsius and 4 degrees Celsius, absolute darkness, and chronic food scarcity. Picture the ocean floor as a massive map, viewed from above. Most of it, 99.75%, stays relatively flat, sitting between 2,000 and 6,000 meters deep. Now imagine that scattered across that map, there are 46 narrow scars where the ground simply disappears. The terrain drops sharply past 6,000 meters, opening into crevices so deep that most land mountains would fit inside them with room to spare. Together, these scars cover an area smaller than the surface of Brazil. Yet they represent the last 45% of the ocean's total depth. All that vertical vastness is packed into a tiny fraction of the ocean floor. Each of these 46 habitats is formally called a Hadal zone, a term coined in 1956 by Danish scientist Anton Brun following expeditions that found living organisms at depths previously believed to be sterile. Before that, the scientific consensus lumped everything below 2,000 meters into a generic category called the abyssal zone. The discovery that distinct organisms lived exclusively at depths above 6,000 meters demanded its own terminology. Hades, the subterranean realm of Greek mythology, inaccessible and permanently dark, provided the fitting name for this domain that resists direct observation. Pressure above 600 atmospheres needs a concrete comparison to make sense. Atmospheric pressure at sea level equals roughly 1 kilogram per square centimeter. At 6,000 meters deep, the column of water above exerts 600 times that force on every surface it touches. Over an area the size of an open palm, about 150 square centimeters, the total pressure exceeds 90 tons. Metal structures built without specific reinforcement would implode instantly. Conventional military submarines, built to withstand considerable pressures, rarely dive past 600 meters, 1/10 of the minimum Hadal depth. Temperatures between 1 degree Celsius and 4 degrees Celsius might seem trivial. After all, household refrigerators operate in similar ranges. However, in this context, the cold is not just discomfort, it's a severe metabolic regulator. Chemical reactions, including those that sustain life, occur exponentially more slowly at low temperatures. Hadal organisms have evolved enzymes and cell membranes adapted to function under this thermal regime, moving any Hadal creature to higher temperatures, even moderate ones by human standards, frequently causes rapid death, as their biological systems were calibrated for an environment most living things would never experience. Absolute darkness is the third unifying condition. Sunlight penetrates the oceans only to about 200 meters deep, a layer called the photic zone. Below that, light diminishes progressively until it fades out around 1,000 meters. The Hadal zone sits 6 times deeper than that limit. No solar photon ever reaches these depths. Photosynthesis is impossible. Plants and algae cannot survive. The entire Hadal food chain ultimately depends on organic matter falling from upper layers. Flakes of decomposed biological material collectively called marine snow, sediments carried by currents, and occasionally carcasses of large marine animals that sink and provide temporary feasts for bottom-dwelling communities. Chronic food scarcity is perhaps the most persistent challenge in this environment. The deeper the Hadal zone, the less organic matter reaches the bottom. During the descent of miles of water column, bacteria and other consumers break down much of the available material. What survives the journey is distributed unevenly, concentrating in certain regions of the trenches, while others remain practically barren for long stretches. Hadal animals have developed strategies such as extremely slow metabolism, the ability to endure long periods of starvation, and in some cases opportunistic habits, rapidly consuming any resource that shows up before competitors can get to it. The 46 habitats differ from one another in dimensions that go far beyond simple depth. Some stretch for hundreds of kilometers in length, like elongated cracks in the ocean floor. Others are relatively compact structures. Some were formed tens of millions of years ago, others are geologically recent. Certain habitats experience frequent earthquakes that periodically reshape their floor and redistribute their inhabitants. Others remain seismically quiet for centuries. These structural differences produce distinct biological communities, species that have specialized to the specific conditions of each trench, without contact with equivalent populations in distant trenches, separated by abyssal plains that function as impassable barriers for organisms adapted to extreme pressures. Geographic isolation between trenches creates evolutionary dynamics comparable to those of oceanic islands on the surface. A species of amphipod, a shrimp-like crustacean common in Hadal environments, found in the Mariana Trench may differ significantly from a related species in the Tonga Trench, separated by thousands of kilometers of ocean floor too shallow for Hadal organisms to cross. Each trench functions as an isolated biological laboratory, where specific adaptations emerge in response to local conditions. This pattern of speciation through geographic isolation, while documented in surface islands, replicates itself in the most inaccessible domain on the planet. The Hadal zone remains the least studied ecosystem on Earth. Technically, accessing these environments is more challenging than exploring lunar surfaces. The pressure that would destroy unprotected equipment requires specially built vehicles whose development consumes decades and considerable resources. Only a handful of crewed missions have reached Hadal depths. Pressure-resistant robots have completed more systematic, but still fragmentary exploration. Each dive reveals unknown organisms, unexpected geochemical processes, and geological structures that challenge previous models. The map of these 46 windows into the planet's interior remains grossly incomplete, a standing invitation for scientific exploration in a world that still holds untouched territories well below the surface we call home. Many of the Hadal zones are located in the western Pacific Ocean. Of the 46 mapped Hadal habitats, 23 are subduction trenches in the Pacific. The Mariana Trench, near Guam and the northern Mariana Islands, at 10,984 meters, is the deepest point on the planet. Right below it on the scale are the Tonga Trench, 10,800 m, near Tonga and Fiji, and the Philippine Trench, 10,540 m. the Kuril-Kamchatka Trench, 10,542 m, off the coast of Russia and Japan, and the Kermadec Trench, 10,047 m, near New Zealand, round out the 5 Hadal habitats that exceed 10,000 meters. Subduction trenches account for 94% of the Hadal zone and function as deposition centers, channeling sediment and organic carbon toward the trench axis. The Western Pacific, where tectonic plate activity is most intense, concentrates the most extreme and most extensive habitat on the planet. To understand why the Pacific dominates this ranking, you need to understand what creates an ocean trench. When 2 tectonic plates collide and one slides under the other in a process called subduction, the ocean floor bends downward, forming V-shaped depressions of exceptional depth. The Pacific is surrounded by active subduction zones, the so-called Ring of Fire, an arc of intense tectonic activity stretching from Chile to Japan, passing through Alaska and the western Pacific Islands. This unique geological configuration positions the Pacific as the natural home of the planet's deepest trenches. The Mariana Trench deserves specific dimensional analysis. At 2,550 kilometers in length with a confirmed maximum depth of around 10,935 meters at the point known as Challenger Deep, named after the British ship HMS Challenger, which conducted the first scientific sounding of the site in 1875, it is the deepest depression ever recorded in Earth's crust. To put that depth in perspective, if Everest, at 8,849 meters, were submerged in this trench, its summit would still be covered by more than 2 kilometers of water. The tallest mountain on the planet would vanish completely. Extreme depth generates extreme pressure in direct proportion. At the bottom of Challenger Deep, the water column above exerts approximately 1,086 bar, equivalent to more than 1,000 times atmospheric pressure at sea level. To put that number in real terms, every square centimeter of surface at the bottom of the Mariana Trench bears the equivalent of about 1 kilogram and 100 grams of force. Multiplied across the total surface area of an average human being, approximately 17,000 square centimeters, the total weight would be around 18 tons distributed evenly across the body. No unprotected biological tissue would survive that compression for even a fraction of a second. The Tonga Trench, the second deepest on the planet, sits in the South Pacific, where the Pacific Plate dives under the Australian Plate. Despite a depth comparable to the Marianas, Tonga presents distinct ecological characteristics, different sediment temperatures, different organic matter deposition rates, different biological communities. The trench stretches roughly 2,500 kilometers along the arc of the Tonga and Fiji Islands. Frequent earthquakes in the region, some of the largest magnitudes recorded globally, periodically reshape this trench's floor and redistribute sediments that built up over decades of slow deposition. The Philippine Trench, though third in maximum depth, stands out for its extent and structural complexity. Formed by the subduction of the Philippine Plate under the Eurasian Plate, it spans a substantial area of the western Pacific Ocean, with multiple subdepressions and internal topographic variations. The biodiversity recorded in this trench includes endemic organisms, species found exclusively in this habitat, with no record in any other trench in the world. Its relative geographic isolation and the specific conditions of the tropical Western Pacific have shaped a unique biological community, partially documented by recent robotic expeditions. The Kuril-Kamchatka Trench off Japan and Russia presents a notable geological feature. It connects topographically to the Japan Trench, forming a continuous Hadal habitat along one of the most seismically active zones on the planet. This geographic continuity contrasts with the isolation characteristic of other Hadal habitats. However, variations in depth, temperature, and nutrient flow along this stretch produce ecological gradients that effectively segment biological communities, even without an absolute physical barrier between them. The result is a sequence of microcommunities adapted to the specific local conditions of each section. The Chromatic Trench, north of New Zealand, rounds out the group of 5 Hadal habitats above 10,000 meters. Studied with relative frequency due to its proximity to New Zealand's scientific infrastructure, this trench has contributed important discoveries to Hadal biology, including records of amphipod crustaceans in unusual abundance and organisms with specific biochemical structures to withstand extreme pressures. Its location in the South Pacific separates it from the Western Pacific trenches by thousands of kilometers of ocean floor. Isolation that, over vast geological timescales, has produced significant biological differentiation relative to neighboring trenches. The fact that 84% of all Hadal habitats are in the Pacific is no geological coincidence. It is a direct consequence of that ocean's tectonic architecture. The Pacific is the oldest and most extensive of the oceans, with an ocean floor denser and colder than the Atlantic floor, and therefore more prone to diving under continental plates at collision zones. While the Atlantic slowly expands, pulling the Americas and Europe apart by centimeters each year, the Pacific contracts as its margins are consumed by subduction. This dynamic produces the belt of trenches that characterizes the Pacific Basin, making it the definitive repository of the planet's greatest depths. The concentration of extreme depths in the Western Pacific creates a singular geographic circumstance. In a relatively compact area between Japan, Guam, the Philippines, and New Guinea, some of the deepest, most studied, and most biologically rich trenches on the planet are found. This region, where tectonic plate movement is simultaneously the most violent and the most productive in terms of extreme habitat formation, functions as the geological core of the global Hadal system. Any serious map of deep ocean geomorphology inevitably returns to this corner of the Pacific as the epicenter of its most remarkable feature. The V-shape of subduction trenches is not merely topographic, it is ecological. The unique V-shaped topography of Hadal trenches promotes a funnel effect that concentrates sediment and organic carbon, facilitated by occasional seismic activity and high-frequency fluid dynamics. In the Japan Trench, 8/12 m, off the coast of Japan, the 2011 Tohoku earthquake delivered more than 1 teragram of organic carbon to the Hadal environment in a single event. Sediments accumulated in trench basins act as organic carbon sinks during interseismic periods. The Isobonin, 9/810 m, Bougainville, 9/103 m, and Volcano, 9/156 m, trenches, all in the Pacific near Japan and Papua New Guinea, inhabit the same dynamic subduction system, where the plate movement that threatens coastal cities is the same one that periodically supplies the deepest floor on the planet with organic matter. Before understanding how earthquakes feed trenches, you need to understand their geometry. A subduction trench in cross-section looks like a pronounced V, sloping walls that converge into a narrow axis. This shape is not static. The angle of the walls, the width of the opening, the slope of the floor all vary from trench to trench and along any single trench. But the physical principle that this geometry activates is constant. Any loose particle on the walls, sediment, organic carbon, rock fragments, gravitates toward the lowest point. The V-shape is literally a permanent funnel pointed at the trench axis. Sediment on ocean slopes accumulates slowly over decades. Fine particles, clay, fragmented biological remains, terrestrial material carried by rivers, settle in layers along trench walls and the platforms surrounding them. This accumulation is fragile. The slope of the terrain keeps sediments in unstable equilibrium. Any disruption, a stronger ocean current, volcanic activity, and especially seismic tremors, can destabilize these layers, turning static deposits into turbidity currents. Underwater avalanches of sedimentary material that raced down the trench walls toward the axis, carrying everything that had been deposited on the surface. The Tohoku earthquake of March 2011, magnitude 9.0, one of the most intense ever recorded, demonstrated this dynamic on an unprecedented documented scale. The seismic violence destabilized sediments that had built up over years along the slopes of the Japan Trench. Sedimentary material rich in organic carbon, plankton remains, degraded plant matter, fragments of marine organisms, was mobilized into turbidity currents that traveled down the trench walls to the axis. When researchers mapped the volume deposited by combining bathymetric data collected before and after the event, the result was unambiguous. More than 1 teragram, 1 million metric tons, of organic carbon had reached the Hadal floor in a single seismic pulse. A teragram of carbon deserves a dimensional comparison. The annual carbon dioxide output of a mid-sized city, say 500,000 residents, hovers around a few tens of megatons of CO2. Elemental carbon in that CO2 represents a fraction of that value. 1 teragram of organic carbon is therefore equivalent to an amount that would take decades of slow deposition to accumulate under normal conditions, delivered in hours by a single geological event. For the Hadal biota of the Japan Trench, that pulse represented an extraordinary, sudden, and temporary feast, followed by a return to the chronic scarcity that defines the environment. The role of the periods between earthquakes deserves equal attention. When no seismic event disrupts the system, sediments continue accumulating on the slopes. Organic carbon deposited in these layers becomes temporarily trapped, sequestered from active oceanic circulation, waiting for the next seismic pulse that will redistribute it. This stop-and-start cycle defines a supply pattern in which the Hadal floor alternates between periods of relative scarcity and sudden abundance events. Hadal species such as giant amphipods respond to these pulses with opportunistic behavior, accelerated reproduction, intense feeding, before returning to slower metabolic rhythms consistent with scarcity. The Isobonin and Volcano Trenches, north of the Marianas, share the same subduction system that has fueled much of the Hadal activity studied in the Western Pacific. The Isobonin Trench, with a maximum depth of nearly 9,810 meters, stretches approximately 1,200 kilometers off the coast of Japan. Its topographic connectivity with other trenches in the system creates conditions for sediment transfer between neighboring habitats, a rare phenomenon in the Hadal zone, where isolation is the rule. The adjacent Volcano Trench sits in a zone of intense submarine volcanic activity that adds inorganic chemical compounds to its floor beyond conventional organic matter. The Bougainville Trench, off Papua New Guinea, with a maximum depth of around 9,103 meters, represents a case of particular ecological interest. Its proximity to the Australian continent and the large Melanesian islands ensures a relatively high input of continental organic matter, plant material and nutrient-rich sediments carried by rivers from tropical islands. Combined with the region's seismic activity, this input produces conditions of relative abundance compared to other trenches in the global Hadal system, with biological densities higher than the average observed in more remote trenches. The connection between coastal seismicity and Hadal nutrition creates a paradox worth stating directly. The same geological process responsible for devastating tsunamis, oceanic plate subduction that triggers megaseismic earthquakes, is the ecological mechanism that periodically rescues the deepest communities on Earth from starvation. The same force that destroyed Japanese coastal cities in 2011, killing nearly 20,000 people, simultaneously mobilized tons of organic carbon that fed ecosystems 8 kilometers deep. The geology that threatens the surface sustains the abyss. This duality is just one of the ironies that make the Hadal Zone one of the most fascinating and least understood domains on the planet. The study of these trenches and their relationship with earthquakes opens an important window into the global carbon cycle. Organic carbon sequestered in the axis of Hadal trenches can remain buried for geological timescales, millions of years, effectively removed from active atmospheric and oceanic circulation. Understanding the rate at which earthquakes mobilize and deposit this carbon is therefore not merely a matter of Hadal biology, but a relevant piece in understanding how the planet regulates carbon over vast periods. The Western Pacific trenches, with their intense seismicity and extreme depths, are privileged natural laboratories for observing this process in its full scale and geochemical consequence. The Pacific Ring of Fire traces the outline of subduction trenches with tectonic precision. The Yap Trench, 8527 m, near Micronesia, and the Palau Trench, 8054 m, between Palau and the Philippines, mark the central sector of the Western Pacific. The New Britain Trench, 8320 m, off the coast of Papua New Guinea, and the Aleutian Trench, 7820 m, between Alaska and Russia, close off the northern arc. On the opposite side of the ocean, the Atacama Trench, 8055 m, off the coasts of Peru and Chile, and the Middle America Trench, 6669 m, which runs along Mexico, Guatemala, El Salvador, Honduras, Nicaragua, and Costa Rica, mark the eastern sector. The New Hebrides, 7570 m, trench, near Vanuatu, the Ryukyu, 7507 m, between Japan and Taiwan, the Banda, 7440 m, in Indonesia, and the San Cristobal, 7155 m, in the Solomon Islands, fill in the intermediate sectors. The geographic isolation of the trenches results in high levels of species endemism, organisms found exclusively in that habitat and nowhere else on the planet. To make sense of this system's map, picture the Pacific like a clock. Following the outline of the clock face clockwise starting from Japan, every arc of volcanic islands marks a subduction zone, and every subduction zone produces trenches. This circuit, called the Ring of Fire, is responsible for about 90% of the earthquakes recorded annually on the planet. Every tremor is the result of an oceanic plate diving beneath another, and it is precisely that dive, built up over millions of years, that carves out the Hadal depressions. The Ring of Fire is not merely a geological boundary. It is the chisel that engraved Earth's greatest depths. The Yap Trench, in the central Western Pacific, has a peculiar geometry, an approximate inverted J shape, stretching roughly 650 kilometers near the island of Yap in Micronesia. It sits on the southeastern edge of the Philippine Sea Plate, between the Palau Islands and the Mariana Trench. Its maximum depth of 8,527 meters places it squarely within Hadal territory, and its relative isolation from adjacent trenches has favored the development of biological microcommunities with their own distinct characteristics. Recent high-resolution mapping revealed that the Yap Trench, contrary to what appeared topographically simple, contains multiple subdepressions separated by intermediate ridges. The New Britain Trench, off Papua New Guinea, stands out as one of the most recently formed subduction zones on the planet, geologically young, with oceanic crust subducting at angles and speeds different from older trenches. This recent tectonic dynamism produces one of the highest seismicity rates among Hadal trenches. At the bottom of this trench, researchers documented large quantities of spoonworms, echiurans, spread across the sedimentary axis. These tubular organisms, which feed on deposited organic material, indicate that the nutrient flow to the bottom of this trench is relatively constant, sustaining dense benthic fauna by Hadal standards. The Aleutian Trench, along the northern arc, stretches approximately 3,700 kilometers, one of the longest on the planet, between Alaska and Siberia. Despite its impressive extent, its maximum depth of around 7,820 meters is moderate compared to the western Pacific trenches. Its location at high latitudes exposes the Hadal habitat to distinct oceanographic dynamics. Colder surface water, greater seasonal biological productivity in upper layers, and consequently a relatively more abundant flow of organic matter to the bottom than in equivalent tropical trenches. This higher nutrient input sustains comparatively denser biological communities along the Hadal axis. The Atacama Trench, in the eastern Pacific off Peru and Chile, reveals the opposite side of the Ring of Fire. Here, the Nazca Plate dives beneath the South American Plate in one of the fastest documented subductions, about 7 to 8 centimeters per year. This subduction rate, beyond building the Andes through continental volcanism, generates one of the most seismically active zones in South America. The trench stretches nearly 3,700 kilometers along the Pacific coast of South America, with a maximum depth close to 8,055 meters. Paradoxically, the Humboldt Current running along this coast produces one of the most biologically productive oceanic zones on the planet, ensuring a relatively generous organic input to the Hadal axis below. The Middle America Trench, with a maximum depth close to 6,669 meters, represents the lower boundary of Hadal territory, barely pushing past 6,000 meters at its shallowest stretch. Formed by the subduction of the Cocos Plate beneath the Caribbean Plate along the entire Pacific coast of Central America, this relatively shallow trench hosts Hadal ecosystems that allow scientists to study the transition between the abyssal and Hadal zones. The lower pressure compared to deeper trenches results in borderline conditions that some generalist organisms can tolerate, enabling direct comparison between shallow trench communities and those in deeper ones, revealing which adaptations are strictly necessary for life above 600 atmospheres. Species endemism is one of the most well-documented biological consequences of isolation between trenches. Species of amphipods from the genus Hirondelia, the dominant crustaceans in virtually every sampled Hadal habitat, show geographically restricted distributions. A species documented in the Kermadec and Tonga trenches is rarely found in western Pacific trenches, and vice versa. Genetic analyses confirm that populations separated by thousands of kilometers of abyssal plain have diverged enough to constitute distinct species. The mechanism is equivalent to what produces unique fauna on oceanic islands. Prolonged isolation combined with specific selective pressures generates independent lineages, even from common ancestors. The topography of the intermediate trenches, New Hebrides, Ryukyu, Banda, San Cristobal, reflects the geological diversity of the Ring of Fire. Each sits in a distinct tectonic context. Different subduction angles, different ages, different seismicity rates. The Ryukyu Trench, between Japan and Taiwan, forms where the Philippine Sea Plate dives beneath the Eurasian Plate, a different system from the subduction that produces the deepest trenches in the Pacific. The Banda Trench, in Indonesia, is embedded in one of the most tectonically complex environments on the planet, where multiple small plates interact simultaneously, producing subduction geometries that still challenge conventional geophysical models. The inventory of trenches along the Ring of Fire reveals that the same geological process that makes the Pacific Basin the most dangerous for coastal populations. High seismicity, frequent tsunamis, widespread volcanism, is also the mechanism that distributes, around the ocean's perimeter, the most extreme and most isolated habitats in the biosphere. From Japan to Peru, passing through the Aleutians, Micronesia, Papua New Guinea, and Central America, subduction trenches mark the outline of a contracting ocean, being consumed along its own edges while maintaining, at its deepest points, ecosystems that have existed and persisted over geological timescales, indifferent to the biological and climatic revolutions that transformed the world above them. 4 trenches complete the Pacific inventory with depths near the Hadal threshold of 6,000 meters. The Manus Trench, 100 m, near Papua New Guinea, and the Pisgah Trench, 300 m, south of New Zealand, occupy the southwestern sector. The Jort Trench, 60 m, in the South Pacific near Antarctica, and the Admiralty Trench, 6000 m, also near Papua New Guinea, sit right at the Hadal Zone threshold. Species richness is relatively stable across trenches, but within each trench it decreases with depth. In the deepest sections, there is only one dominant group, lichenozoid amphipods, ubiquitous in every Hadal trench sampled to date. In the shallower trenches of the Pacific inventory, this pattern still holds. Scavenging amphipods arrive at any carcass that sinks to the bottom before any other group does. The 6,000-meter threshold that defines the entrance to the Hadal Zone is not arbitrary, but it is not absolute either. It represents a scientific convention based on observations of changes in biological communities and physical-chemical conditions around that depth. The pressure at this point, approximately 600 atmospheres, appears to constitute a real physiological barrier for several groups of organisms. Species that inhabit the abyssal zone, immediately above this threshold, generally do not descend past it. However, the boundary is not a wall, it is a gradient. Trenches that barely exceed 6,000 meters allow scientists to study exactly this transition. Which organisms cross the threshold, which ones turn back, which ones never show up. The Manus Trench, near Papua New Guinea with a maximum depth of about 6,100 meters, sits in a basin formed by extensional tectonics, different from conventional subduction trenches. The Manus Basin results from a process in which oceanic crust is being actively pulled apart, creating new ocean floor. This different geological origin produces hydrothermal characteristics, heat sources and chemical compounds rising from the interior of the crust that influence water chemistry near the bottom and potentially the biological communities established there. The combination of hadal depth and hydrothermal activity creates unusual conditions in the context of the global hadal system. The Pisgah Trench, south of New Zealand, marks the southern boundary of hadal trenches in the southwestern Pacific sector. Formed by the subduction of the Australian plate beneath the Pacific plate, this relatively small structure extends for a few hundred kilometers. Its location at high latitudes, near 46 degrees south, exposes it to subantarctic oceanographic dynamics, cold waters, intense deep currents, and seasonal variations in organic matter input different from tropical trenches. New Zealand's proximity has facilitated scientific expeditions that documented its fauna, including amphipods, isopods, and polychaetes adapted to the specific conditions of this high-latitude trench. The Jort Trench, near Antarctica in the South Pacific, represents an extreme case of isolation. Situated well beyond conventional shipping routes, it receives only sporadic scientific attention. Its depth of about 6,060 meters positions it right at the lower edge of the Hadal Zone. The waters surrounding it are among the coldest and most oxygenated on the planet. The Antarctic Ocean, driven by intense winds and currents, produces bottom water that oxygenates the world's ocean floors. Paradoxically, this excessive oxygenation combined with temperatures near freezing creates a physiologically demanding environment even by Hadal standards, where extreme cold slows down every metabolic reaction. The Admiralty Trench, also near Papua New Guinea with a depth right at the Hadal boundary, stands out for its very small total area, among the smallest of all catalogued Hadal trenches. Hadal habitats with very small areas impose additional constraints on the populations that inhabit them, less absolute substrate available, smaller volume of Hadal water, and consequently smaller population sizes. Smaller populations are more vulnerable to local extinctions caused by stochastic events, random fluctuations in food supply, isolated seismic disturbances, changes in currents. The Admiralty Trench illustrates the lower viability limit as an independent Hadal habitat. Lichenozoid amphipods, whose name derives from the superfamily Lichenozoidea, deserve detailed attention for their absolute dominance in the deepest sections of any trench. These crustaceans, superficially resembling shrimp but belonging to a distinct order, have developed a set of adaptations that make them the standout champions of the Hadal habitat. Their ability to detect food at considerable distances using sensitive chemoreceptors allows them to locate carcasses and other food resources in absolute darkness. When they reach a food source, highly distensible stomachs allow them to consume enormous quantities in a short window of time, an opportunistic strategy that maximizes the use of scarce and unpredictable resources. The arrival of amphipods at any carcass that sinks to the Hadal floor is a phenomenon documented by cameras installed on submerged bait landers. Within hours of a carcass reaching the bottom, hundreds, sometimes thousands, of amphipods converge on it, drawn by the chemical plume dispersing through the water. The consumption process is fast. The bones of medium-sized fish can be picked clean within days. This speed of response, even in an environment where movement should be slowed by extreme pressure, reveals deep biochemical adaptations. Specific enzymes, cell membranes reformulated with stabilizing compounds such as trimethylamine oxide, that allow normal functioning under conditions that would immobilize non-adapted organisms. The distribution of lichenozoid amphipods across all sampled Hadal trenches, Marianas, Tonga, Kermadec, Japan, Atacama, Puerto Rico, among others, makes up the only truly cosmopolitan distribution pattern documented in the Hadal zone. While most Hadal species are endemic to a single trench or group of adjacent trenches, certain lichenozoid species display broader distributions, raising a relevant evolutionary question. How do strictly Hadal organisms, unable to survive the lower pressures of the abyssal zone, cross the thousands of kilometers of abyssal plains separating distinct trenches? The answer is not yet fully known, but it likely involves passive dispersal on deep currents and occasional tolerance of pressure variations during larval stages. The existence of trenches at the Hadal threshold, such as Manus, Pisgah, Jort, and Admiralty, offers a scientific perspective that very deep trenches cannot provide. The ability to directly compare communities at depths slightly above and below the 6,000-meter threshold. This comparison reveals which adaptations are a necessary condition for inhabiting the Hadal zone, and which are additional refinements that organisms in deeper trenches develop progressively. The complete inventory of the Hadal system, from the shallowest to the deepest, makes up an atlas of biological adaptation to extreme conditions, a natural document that records, in living organisms, the evolutionary history of the conquest of the most inhospitable environments on the planet. While the Pacific holds more than 20 subduction trenches, the Atlantic has just one. The Puerto Rico Trench, 8408M, near Puerto Rico and the Dominican Republic, the deepest point in the Atlantic. It was there that, in 1970, the deepest fish ever recorded was caught, Abyssobrachla galathei, at 8,370 meters. The Atlantic makes up for its lack of subduction trenches with deep transform faults. The Cayman Trough, 8126M, in the Caribbean Sea between Jamaica, Cuba, and Belize, is the second deepest Hadal structure in the Atlantic. The Romanche Fracture Zone, 715M, in the equatorial Atlantic between Brazil and Ghana, offsets the Mid-Atlantic Ridge by 900 kilometers, making it the largest equatorial fracture zone in the Atlantic, and serves as the main conduit for the flow of Antarctic bottom water between the western and eastern Atlantic basins. The Atlantic is a young ocean on a geological scale. It opened roughly 180 million years ago when the supercontinent Pangaea broke apart, separating the Americas from Africa. Unlike the Pacific, which is surrounded by active subduction zones consuming its edges, the Atlantic is expanding. The mid-Atlantic ridge continuously produces new oceanic crust, pushing the continents in opposite directions. This expansive regime does not favor the formation of subduction trenches. For a trench to form, one plate must dive beneath another, and in the Atlantic that only happens at one localized point, the Lesser Antilles Arc, where the Caribbean plate meets the North American plate. The Puerto Rico Trench, the product of that localized subduction, reaches a maximum depth of about 8,408 meters, making it the deepest point in the Atlantic and the 8th deepest on the planet. Its location near Puerto Rico, on the northern edge of the Caribbean Sea, puts it surprisingly close to densely populated coastlines. Less than 100 kilometers separates the northeastern beaches of Puerto Rico from this trench's axis. This proximity has real-world implications. Tsunamis generated by earthquakes in the Puerto Rico Trench could hit Caribbean coasts in very little time, making the monitoring of this structure geologically relevant to the safety of the region's populations. The capture of Abyssobrachylogalathea in the Puerto Rico Trench in 1970 remains one of the most cited records in hadal biology, and also one of the most contested. The specimen was caught by trawling, a method that lowers an open net and retrieves it open as well, making it impossible to guarantee with certainty that the fish was collected at exactly the recorded depth. Some researchers suggest it may have been caught during the ascent of the net at a shallower depth. Despite this methodological caveat, the record remains formally recognized. The fish in question is a cusk eel, a long, scaleless organism with vestigial eyes and a gelatinous body adapted to the absence of light and extreme pressures. The Cayman Trough in the Caribbean Sea represents a different geological category than the Puerto Rico Trench. While the trench is a product of subduction, one plate diving under another, the Cayman Trough is a transformed fault, two plates sliding horizontally relative to each other, with the lateral movement creating stresses that eventually open deep vertical depressions. The 8,126-meter depth of the Cayman Trough makes it the deepest known transformed fault on the planet. Its location in the Caribbean, relatively close to the surface, has facilitated expeditions that documented biological communities distinct from those found in subduction trenches, including traces of hydrothermal activity along the fault edge. The Romanche fracture zone in the equatorial Atlantic has an oceanographic function that goes beyond its relevance as a hadal habitat. The Mid-Atlantic Ridge, the underwater mountain range that runs through the Atlantic from north to south like a backbone, normally acts as a barrier to bottom currents. Antarctic bottom water, formed near Antarctica when super-chilled, dense surface water sinks to the ocean floor, flows northward through the western Atlantic. To cross to the eastern side of the ocean, it needs an opening in the ridge. The Romanche fracture zone is, at depth, the main opening, a channel that allows this cold, dense current to supply the floor of the eastern Atlantic with oxygenated water. This role as an oceanic conduit gives the Romanche fracture zone an importance that goes well beyond hadal biology. Thermohaline circulation, the global system of ocean currents driven by differences in temperature and salinity, depends on the continuous flow of Antarctic bottom water to maintain the oxygenation of ocean floors worldwide. Interrupting that flow would have consequences for global circulation. The Romanche fracture zone, with its roughly 7,715 meters of maximum depth, is simultaneously an isolated hadal habitat and a strategic passage in the planet's plumbing, a channel connecting oceanic basins separated by the world's largest submerged mountain range. The contrast between the Atlantic and the Pacific in terms of Hadal structures reflects fundamentally different geological histories. The Pacific is shrinking, consumed at its margins by subduction that produces trenches. The Atlantic is growing, expanded by the ridge that produces new crust. This difference in tectonic regime implies that, on a future geological timescale, the Atlantic could eventually develop more subduction zones along its margins, and with them, new Hadal trenches. However, on a human timescale, the Atlantic will remain essentially as it is. An ocean with three Hadal structures, profoundly different from the Pacific in geomorphological complexity, but equally fascinating in the biological adaptations sheltered by its depths. The discovery that the Atlantic maintains specific Hadal fauna, including species endemic to the Puerto Rico Trench not recorded in Pacific trenches, demonstrates that even with scarce Hadal structures, the ocean has generated, over millions of years, biological lineages adapted to the specific conditions of each habitat. The isolation of the Puerto Rico Trench from the Pacific trenches, separated by thousands of kilometers of abyssal plain and the barrier of the Americas, guaranteed enough biological divergence to produce endemism. The Atlantic, with only three Hadal structures, confirms that prolonged isolation and extreme selective pressure are sufficient to generate unique biodiversity, regardless of the number of available habitats. The total area occupied by Hadal depths in the southwestern Pacific and eastern Indian Ocean is 716,915 square kilometers, with 58% in trenches, 37% in basins and troughs, and 5% in fracture zones. Troughs, elongated structures wider and less steep than subduction trenches, are Hadal habitats that are frequently overlooked. The South Sandwich Trench, 8 m, in the Antarctic Ocean near the British islands of the same name, and the South Orkney Trench, 6 m, represent the Antarctic sector. In the Indian Ocean, the Java Trench or Sunda Trench, 7 m, between Indonesia and Australia, is the only subduction trench in the ocean, and the deepest in the Indian Ocean. The Diamantina Fracture Zone, 7,099 m, near Western Australia, and the Vima Fracture Zone, 6,492 m, near the Maldives and Seychelles, round out the fracture zones of the Indian Ocean. The distinction between a subduction trench, a trough, and a fracture zone matters both geologically and ecologically. A subduction trench has a pronounced V-shaped profile, steep walls, and a narrow axis, the direct product of an oceanic plate diving under another. A trough is a wider structure, with less vertical walls and a broader floor, generally formed by different processes: rifting, basin subsidence, or thick sedimentary deposition filling natural depressions. Fracture zones are linear cracks produced by the horizontal movement of plates along transform faults. Each geometry creates distinct microclimates, different deposition patterns, and consequently biological communities with their own characteristics. The South Sandwich Trench, in the Antarctic Ocean, forms where the South American Plate meets the South Sandwich Plate at an isolated volcanic arc. With a maximum depth close to 8,428 meters, it is the deepest Hadal trench outside the Pacific after the Puerto Rico Trench in the Atlantic. Its location at extremely high latitudes, near 56 degrees south, subjects it to Antarctic oceanographic conditions. Very low bottom temperatures, intense circumpolar currents, and more pronounced seasonal variations in surface productivity than in tropical trenches. The circulation of the Antarctic circumpolar current influences the transport of organic matter to Hadal depths in this region. The South Orkney Trench, with a depth of only about 6,022 meters, represents a borderline Hadal habitat in the Antarctic sector. Analogous to the Manus, Jort, and Admiralty trenches in the Pacific in terms of proximity, to the Hadal threshold. Its geographic proximity to the South Sandwich Trench, in the same region of the Antarctic Ocean, creates a comparative opportunity. Two nearby Hadal habitats, at different depths, subject to the same regional oceanographic conditions, but with different pressures along their axes. Comparing the biological communities of these two trenches allows scientists to isolate the effect of depth from the shared regional environmental variables. The Java Trench, also known as the Sunda Trench, is geologically significant for a reason that goes beyond its Hadal depth. The subduction that produces it was the same one that generated the Indian Ocean earthquake and tsunami of December 2004, one of the most destructive seismic events in recorded history. The Indo-Australian Plate dives beneath the Eurasian Plate along a subduction zone that creates the Java Trench. The same process that carved this Hadal habitat over millions of years released, in a single moment in 2004, enough energy to kill more than 220,000 people on the shores of the Indian Ocean. The trench and the tsunami share the same geological cause, separated only by timescale. The Diamantina Fracture Zone, off the southwestern coast of Australia, is a fracture zone formed by the horizontal movement of plates along an ancient transform fault. With a maximum depth close to 7,099 meters, it represents a Hadal habitat in an ocean, the Indian, that has scarce and relatively understudied Hadal structures. Expeditions that sampled the Diamantina Fracture Zone found biological communities with characteristics distinct from Pacific trenches, potentially reflecting both prolonged isolation and the specific oceanographic conditions of the eastern Indian Ocean, where currents, temperatures, and surface productivity patterns differ from the Pacific. Troughs as a Hadal category deserve specific attention because they are frequently left out of inventories that focus only on subduction trenches. The largest Hadal trough on the planet, the Wharton Basin in the eastern Indian Ocean, covers more than 218,000 square kilometers of depths above 6,000 meters. That number contrasts sharply with the typical area of a subduction trench. The Mariana Trench, the most famous and studied, has a Hadal area of about 80,000 square kilometers. The Wharton Basin is more than twice as large and virtually ignored in Hadal studies, partly because its wide, less dramatic geometry does not draw the same attention as V-shaped trenches. The distribution of 37% of the Hadal area across basins and troughs implies that most published studies on the Hadal zone focus on less than 2/3 of the actual habitat. Troughs present distinct challenges for exploration. Their vast area makes representative sampling difficult. Less abrupt topography may limit the funnel effect that concentrates organic matter in trenches, and a lower maximum depth reduces the degree of physiological specialization observed in the deepest trenches. However, the extent of these troughs means they represent a significant share of the organic carbon sequestered in the deep ocean floor, relevant to the global carbon cycle. The Vima Fracture Zone in the Indian Ocean, near the Maldives, represents another Hadal fracture zone in an ocean little studied in this context. With just over 6,492 meters of maximum depth, it sits at the Hadal threshold, and in a region oceanographically influenced by the Indian monsoon, the seasonal system of winds and currents that dramatically shifts the Indian Ocean surface productivity between summer and winter. This pronounced seasonal variation may create more clearly defined food pulses for the Hadal floor than in trenches in oceanographically more stable regions. Testing in a different way the foraging strategies and energy storage of benthic organisms. The complete map of Hadal habitats, trenches, troughs, and fracture zones distributed across the Pacific, Atlantic, Indian Ocean, and Antarctic Ocean reveals that the planet's deepest points are not geographic accidents scattered randomly. They are surface expressions of a dynamic planet, whose moving interior continuously shapes and reshapes the outer shell. Every Hadal habitat is the scar of a tectonic collision, the opening of a fault, or the sinking of a basin, processes that operate over timescales of millions of years, indifferent to the brevity of the biological occupation that has taken root along their axis. The 46 windows open to the planet's interior remain, for the most part, unvisited, unmapped in detail, and not yet fully understood, waiting for enough technology and curiosity to reveal what lies at the deepest limit of the biosphere. Hadal troughs exist independently of convergent tectonic plate movement. They are deep depressions that reach 6,000 meters through other geological processes. In the Atlantic, the Canary Trough, 7,268 m, near the Spanish islands in Morocco, the Agulhas Trough, 6,787 m, and the South African Trough, 6,509 m. Both near South Africa, the Argentine Trough, 6,859 m, the North American Trough, 6,922 m, the Essi Atlantic Trough, 6,559 m, between Angola and Namibia, and the Zeleni Mice Trough, 6,000 m, off the coast of Guinea and Senegal, form a chain of Hadal habitats dispersed throughout the Atlantic. In the Pacific, the Central Pacific Trough, 8,211 m, near Kiribati, the NW Pacific Trough, 8,565 m, off the coast of Japan, and the Philippine Trough, 7,872 m, reach depths comparable to those of subduction trenches, without being generated by them. The distribution of food differs between flat trenches and neighboring abyssal plains. The unique topography of the trenches, combined with seismically induced sediment slides, is central to creating this unique environment in which the Earth's deepest organisms survive. An oceanic trough differs from a subduction trench in origin, but not necessarily in depth. While a trench is born from one plate diving under another, a trough forms through other mechanisms. Subsidence of old, dense oceanic crust that sinks under its own weight. Incomplete rifting that opens depressions without fully separating the plates. Sedimentary accumulation in basins that were tectonically lowered in the past and remain as residual depressions. The topographic result can be just as deep, as the NW Pacific troughs demonstrate, reaching 8,565 meters without any active subduction along their axes. Depth and geological origin are, therefore, independent variables. The Canary Trough, off the Canary Islands and the Moroccan coast at a depth of about 7,268 meters, represents one of the Hadal habitats best positioned geographically for European scientific exploration. Its relatively close location to Iberian and African research infrastructure has facilitated expeditions that documented its fauna. Notably, it was in the vicinity of this region of the North Atlantic that Jacques Cousteau took the first photographs ever captured of the Hadal zone in 1956, in the Romanche fracture zone, revealing to the world that the deepest abyss was not sterile, but inhabited by organisms that defied every expectation about the limits of life. The South Atlantic troughs, the Agulhas, South African, Argentine, North American, and Essi Atlantic, form a scattered set that demonstrates how Hadal depths can be reached even in an expanding ocean without dominant subduction. The Argentine Trough, with a depth close to 6,859 meters, sits off the Argentine coast in a deep sedimentary basin formed by processes different from those of the Pacific trenches. Its fauna, potentially endemic due to prolonged isolation from the rest of the Atlantic Hadal system, remains poorly studied, a reflection of the general scarcity of Hadal expeditions in the South Atlantic compared to the attention devoted to the Pacific. The North American Trough, at about 6,922 meters deep, occupies a particular geographic position. In the North Atlantic, the largest oceanic basin in the Northern Hemisphere. Its formation is associated with the subsidence of old oceanic crust in the abyssal region of the North American basin. Like all Hadal troughs, its wider geometry compared to subduction trenches affects the pattern of organic matter accumulation. Without the steep walls characteristic of V-shaped trenches, the funnel effect is less pronounced. However, bottom currents running through the North Atlantic can concentrate sediment along the axes of these troughs, creating conditions of relative food abundance even without convergent topography. Pacific troughs reaching depths of 8,000 meters or more without active subduction represent a finding that initially surprised geophysicists. The NW Pacific Trough, at 8,565 meters, a depth comparable to several cataloged subduction trenches, sits off the coast of Japan in a region of very old oceanic crust. Oceanic crust ages and cools progressively as it moves away from the ridge where it was created. As it cools, it becomes denser and literally sinks, creating depressions without any formal subduction occurring. The Western Pacific contains the oldest and densest oceanic crust on the planet, and consequently some of the deepest basins outside subduction zones. The Philippine Trough, at about 7,872 meters, adjacent to the Philippine Trench, demonstrates that in the complex tectonics of the Western Pacific, subduction trenches and Hadal troughs can coexist in the same region. The separation between these two types of habitat in the same geographic area creates a comparative opportunity. Populations of Hadal organisms in neighboring structures of distinct geological origin, subject to similar oceanographic conditions but with different topographies, allows scientists to isolate the effect of habitat geometry from the shared regional environmental variables. The funnel effect, concentration of organic matter along trench axes, operates differently in troughs and subduction trenches. Studies measuring oxygen consumption in Hadal axis sediments found biological activity up to 2.5 times higher than in neighboring abyssal plains, even considering that the Hadal axis sits thousands of meters deeper. This paradox, more life at the deepest point, farthest from the food source at the surface, is resolved by topography. Any organic particle falling near a trench tends to slide gravitationally toward the axis. Geometry concentrates what distance dilutes, reversing the expected gradient of biomass decreasing with depth. Seismic sediment slides amplify this effect periodically. On the abyssal plains neighboring Hadal trenches and troughs, sediments accumulate in stable horizontal layers for decades. On the slopes of these structures, the same sediment accumulates in unstable equilibrium on inclined surfaces. Any disturbance, an earthquake, a stronger current, internal instability within the layers, triggers underwater avalanches that transport years of accumulated organic material to the axis within hours. The result is a pulse-driven supply regime, long periods of slow deposition interspersed with sudden abundance events, a pattern to which Hadal fauna appears adapted through flexible metabolisms and opportunistic behavior. The distribution of Hadal troughs throughout the Atlantic, from the Canaries to southeastern Africa, passing through Argentina and the Caribbean, reveals that Hadal depths are not the exclusive domain of the seismically active Pacific. In geologically quieter oceans, other processes, subsidence, ancient rifting, deep sedimentary basins, produce habitats equivalent in pressure and darkness. The life that colonized these habitats arrived at some point in the geological past from shallower depths, and adapted, generation after generation, to the specific conditions of each trough. The result, after millions of years of isolation, is biologically distinct communities inhabiting geologically distinct structures, unified only by the physical conditions that define the Hadal zone: extreme pressure, permanent cold, and the total absence of sunlight. In the Indian Ocean, 3 troughs complete the Hadal inventory: the Madagascar Trough, 7,113 m, between Madagascar and Mozambique; the South Australian Trough, 6,000 m, and the West Australian Trough, 6000m, both near Australia. From an ecological standpoint, Hadal communities are frequently endemic to individual or adjacent features, partitioned and isolated by geomorphological structures. The Emperor Fracture Zone, 8103m, in the North Pacific near Russia and Japan, and the Muso Trench, 7208m, near Papua New Guinea, complete the fracture zones of the Pacific. The isolation that separates one trough from the others is not merely geographic, it is evolutionary. The boundaries of these trenches create something resembling an island. Virtually no species can move between them. This reproductive isolation generates the same processes observed on oceanic islands. Species that exist exclusively there, with no representatives anywhere else on the planet. To understand Hadal isolation, it helps to compare it to the isolation of oceanic islands on the surface. A bird species on a remote island, say, Darwin's finches in the Galapagos, cannot cross oceans to breed with populations on neighboring islands. Over generations, local selective pressures shape specific traits until populations diverge enough to constitute distinct species. In the Hadal zone, the mechanism is identical, but the ocean that isolates is not one of surface water. It is ocean floor with insufficient pressure to support strictly Hadal organisms. The abyssal plain, at 4,000 or 5,000 meters, is inaccessible to creatures adapted to 6,000 meters or more. The abyss separates the abyss. The Madagascar Trough, with a depth close to 7,113 meters, sits in the Mozambique Channel, a relatively shallow strait separating Madagascar from the African continent. The location of this trough in an important oceanographic passageway implies exposure to specific currents that carry organic material produced in the tropical waters of the western Indian Ocean. Madagascar, with its extraordinary surface biodiversity and millions of years of evolutionary isolation, stands out as a possible analogy for the trough on its oceanic flank. Both the island and the trough represent isolated habitats where unique life established itself on its own terms, indifferent to the exchanges occurring in the continuous systems around them. The South Australian and West Australian troughs, both with depths close to the Hadal threshold of 6,000 meters, sit around one of the most isolated continents on the planet. Australia is surrounded by oceans that have produced, along its Hadal perimeter, poorly studied structures. The Australian continental shelf extends for hundreds of kilometers in certain directions before plunging into abyssal depths. The Hadal troughs bordering this continent receive organic matter from a zone of biological production different from the tropical trenches of the Western Pacific. This distinct oceanographic context suggests biological communities with their own characteristics, a hypothesis partially confirmed by expeditions that found fauna with a different composition from the most studied trenches. The Emperor Fracture Zone, with a depth of about 8,103 meters in the North Pacific near Japan and Russia, takes its name from the Emperor Seamount Chain, a sequence of extinct volcanoes that marks the trail of the Pacific Plate over a mantle hotspot, the same geological origin that produced the Hawaiian Islands. The transform fault associated with this chain created a significant Hadal depression in a subpolar oceanographic environment, cold waters, high seasonal productivity, substantial organic matter input to the floor. This combination of Hadal depth with relatively abundant nutrition may sustain denser biological communities than similar troughs in oligotrophic tropical regions. The Muso Trench, near Papua New Guinea with a depth close to 7,208 meters, is located in one of the most tectonically complex environments on the planet, the region where multiple microplates interact at the junction of the Pacific, Australian, and Philippine plates. This tectonic complexity implies frequent and varied seismicity, creating conditions for periodic redistribution of sediments along this fault's axis. The proximity of Papua New Guinea, a continental island with large rivers that carry terrestrial organic matter to the ocean, ensures a supply of continental organic carbon, in addition to the marine carbon deposited by the organic snow from the waters above. Evolutionary isolation in Hadal habitats produces biological consequences that go beyond endemic species. Enzymes, proteins that catalyze biochemical reactions in cells, function optimally at specific pressures and temperatures. Enzymes from surface organisms lose function at Hadal pressures. The same metabolic reactions that sustain life on land would collapse at 600 or more atmospheres. Hadal organisms possess modified versions of these enzymes, with slightly altered three-dimensional structures that maintain flexibility and function under extreme compression. These biochemical modifications, accumulated over generations of selection in an environment of constant pressure, are the exclusive evolutionary heritage of each Hadal lineage, impossible to transfer between trenches through simple migration. Beyond enzymes, Hadal organisms accumulate stabilizing compounds called compatible osmolytes. The most studied is trimethylamine oxide, TMAO, present in increasing concentrations with depth in the tissues of Hadal fish. This compound, whose distinctive odor identifies fresh marine fish, stabilizes proteins under high pressure, preventing them from deforming and losing function. Fish from shallower regions have less TMAO. Hadal fish accumulate so much of it that their taste would be intensely ammoniacal to the human palate. The concentration of TMAO increases linearly with the maximum depth of each species, and appears to impose a physical limit on the depth that vertebrates can inhabit. Above about 8,200 meters, the required concentration of TMAO would make the intracellular environment osmotically incompatible with life. The convergence of geographic isolation, extreme pressure, and food scarcity, variables that operate simultaneously in all Hadal troughs and trenches, produces what could be called a natural laboratory of intense selection. Organisms that arrived in these habitats in the geological past, possibly during periods when oceanographic boundaries were different, became trapped when conditions changed. Subjected to continuous selective pressures in an environment with no escape routes, they developed specific adaptations that made them progressively more capable of surviving in the Hadal zone and progressively less capable of surviving outside it. The isolation that was initially accidental became constitutive, an integral part of the biology of each lineage, written into enzymes, membranes, and stabilizing molecules that only make sense at the 46 points on the planet where the ocean floor drops below 6,000 meters. The total area occupied by the 46 Hadal habitats is less than 0.25% of the ocean floor. But these 46 points distributed across the Pacific, Atlantic, Indian, and Antarctic oceans make up the deepest, most isolated, and least explored ecosystem on Earth. 23 subduction trenches in the Pacific, 1 in the Atlantic, 1 in the Indian Ocean, 2 in the Antarctic Ocean, 6 transform faults, 13 Hadal troughs, each with pressure above 600 atmospheres, temperature close to zero, no sunlight, separated from the others by abyssal plains spanning thousands of kilometers. Occasional seismic activity and high-frequency fluid dynamics facilitate the periodic supply of organic carbon to trench axes. The same tectonic system that moves plates and generates earthquakes is the one that feeds these ecosystems. The Hadal zone accounts for 45% of the ocean's total depth range, concentrated in less than 0.25% of its area. And at the 46 points where the ocean floor sinks below 6,000 meters, from the Marianas to the South Orkneys, from the Romanche to the Australian troughs, there is life, adapted, endemic, and functional. Looking at the complete inventory of the 46 Hadal habitats as a unified system reveals a fundamental asymmetry. Almost all extreme depth is concentrated in a stretch of the western Pacific, where tectonic plate activity is most intense. But Hadal life is not confined to that core. Troughs in the South Atlantic, faults in the Indian Ocean, trenches in the Antarctic Ocean. At each of these points geographically remote from the Pacific core, organisms colonized the habitat, adapted to the conditions, and over sufficient geological time, diverged until they constituted unique lineages. Life did not wait for conditions to be perfect. It occupied every depression deep enough that the planet had to offer. The pressure above 600 atmospheres that unifies all 46 habitats has a universal biochemical implication. Any organism inhabiting the Hadal zone needs to solve the same fundamental problem of stabilizing proteins and membranes under extreme compression. The solutions found by independent lineages in Pacific trenches, Atlantic troughs, Indian Ocean faults are convergent in principle but distinct in detail. Comparing the biochemical solutions of Hadal organisms from geographically isolated trenches means studying convergent evolution in real time. Identical selective pressures applied to different ancestors producing similar, but not identical solutions. Temperatures close to zero in all 46 habitats impose a uniform metabolic regime. Biochemical reactions in cold-blooded organisms, a category that includes virtually all Hadal fauna, occur at rates determined by ambient temperature. At 1 degree Celsius or 2 degrees Celsius, reactions are slow, growth is slow, reproduction is slow, response to disturbances is slow. Organisms that live for decades or centuries instead of years. Populations that renew themselves over timescales that no direct scientific observation can fully track. When underwater cameras record amphipods rapidly consuming carcasses, they are documenting exceptional behavior, the emergency response to a rare resource. The rest of the time, metabolism crawls along at a geological pace. The absence of sunlight in all 46 habitats means that no photosynthesis sustains food chains locally. All the energy circulating in the Hadal system arrives from above, as slowly settling organic snow, as seismic pulses of sediment, as carcasses that occasionally sink. This energy dependence on upper layers makes the Hadal system sensitive to any change in surface ocean productivity. During past geological periods of lower oceanic productivity, ice ages that restricted circulation, extinction events that reduced marine biomass, Hadal habitats must have experienced even more severe scarcity. The current communities are descendants of lineages that survived those periods, carrying adaptations to extremes even more intense than those observed today. Separation between habitats by thousands of kilometers of abyssal plain creates isolation that operates differently for each taxonomic group. Bacteria and archaea, single-celled microorganisms without a thick cell wall, can potentially disperse through deep ocean currents, carried passively by flows that traverse the entire planet. Distinct bacterial species found across multiple distant trenches suggest that microbial dispersal crosses barriers that would be impassable for larger organisms. Amphipods and fish, in contrast, are effectively confined to the trenches they inhabit, with no ability to cross abyssal plains at pressures incompatible with their physiology. The Hadal system is therefore permeable to microorganisms and impermeable to metazoans, a distinction with profound consequences for the biogeography of these ecosystems. The Hadal zone as a carbon reservoir has added another dimension to its scientific relevance. Sediments accumulated along trench axes contain organic carbon sequestered from active circulation for periods that can exceed millions of years, especially in subduction trenches, where material deposited on the ocean floor is eventually carried into the Earth's mantle by the subducting plate. Carbon that entered the ocean as atmospheric CO2 was fixed by photosynthetic organisms at the surface, sank as debris, was buried in the axis of a trench, and subducted, completed a cycle that permanently removes it from the atmosphere on a human timescale. Hadal trenches play a part, modest but real, in the long-term regulation of atmospheric composition. The exploration of the 46 habitats remains profoundly incomplete. Fewer than a dozen have been sampled with modern high-resolution equipment. Most have been visited rarely or never. Every expedition that reaches one of these points returns with species new to science, organisms that existed and evolved without any human observer ever knowing of their existence. In 2025, studies published in the journal Cell identified more than 7,000 new microbial species in the Mariana Trench alone, 89% of them previously unknown to science. That result, from a single trench, the most studied of them all, puts into scale the knowledge gap that exists for the remaining 45. Of the 46 points where the ocean floor retreats below 6,000 meters, each is simultaneously the endpoint of a geological process and the beginning of a biological story. Tectonics opened the crack, the ocean filled it, life colonized it. These three processes, geological, oceanographic, and biological, operate on radically different timescales, but converge along trench axes in a unique synthesis. The planet that carved these abysses with plate collisions also provided, through the same movements that caused tsunamis and earthquakes, the organic matter that sustains the deepest communities in the biosphere. From the Marianas to the Australian troughs, from the Pacific arcs of fire to the quiet faults of the Indian Ocean, the 46 Hadal habitats make up the most complete portrait available of what life is capable of enduring, and of how the planet, in its permanent dynamism, keeps creating conditions for that portrait to always be, at least a little, different from what it was before.